Python is the undisputed king of artificial intelligence. But Python alone isn't enough. Its true power comes from the holy trinity of data science, NumPy, Pandas, and Matplotlib. Together, they form the toolkit of every AI engineer. We begin with NumPy, the foundation. Standard Python lists are slow. NumPy introduces the array, which is a high-performance, C-based array structure. It allows for vectorization, performing math on entire blocks of data simultaneously without writing slow loops. In AI, weights and biases are almost always stored as NumPy arrays. Next is Pandas, the Swiss Army knife of data manipulation. It takes the raw power of NumPy and wraps it in a user-friendly structure called the data frame. Think of a data frame as an Excel spreadsheet on steroids. It allows you to clean messy data, handle missing values, and merge massive datasets with just a few lines of code. It is where 80% of an AI project's time is spent, preparing the data for the model. Finally, we have Matplotlib, the eyes of your project. Data in a table is hard to read. Matplotlib allows us to visualize trends, outliers, and distributions. From simple line plots to complex heat maps, it helps us verify that our data is correct and that our AI model is actually learning. In a real AI pipeline, these three work in perfect harmony. You use Pandas to load and clean your data, NumPy to convert it into mathematical tensors for the model, and Matplotlib to plot the training loss and accuracy. Mastering these libraries is the first step toward building the future with AI. Thanks for watching. Welcome to the world of linear algebra. It is the mathematical language of shapes, rotations, and most importantly, artificial intelligence. We begin with the most basic building block, the vector. To a physicist, a vector is an arrow in space with a specific magnitude and direction. To a computer scientist, it is simply an ordered list of numbers. In a two-dimensional plane, a vector connects the origin to a point, like 3, 4. When we group these vectors together into a grid, we get a matrix. A matrix isn't just a container for data, it is a dynamic operator. Multiplying a vector by a matrix transforms the space itself, scaling it, rotating it, or shearing it. But why stop at 2 dimensions? This brings us to tensors. A scalar is a zero-rank tensor, just a single point. A vector is rank 1, a line. A matrix is rank 2, a surface. And a 3-dimensional block of data is a rank 3 tensor. Tensors are the multi-dimensional arrays that flow through neural networks, which is why we call it TensorFlow. Finally, we reach the crown jewel of linear algebra, eigenvalues and eigenvectors. When a matrix transforms space, most vectors get knocked off their original line. But a few special vectors, the eigenvectors, stay exactly on their original span, they are only scaled. The amount they are scaled by is called the eigenvalue. This concept allows us to simplify complex systems, from Google's PageRank algorithm to facial recognition. From simple arrows to high-dimensional tensors, linear algebra is the engine of the modern world. Thanks for watching. Calculus is the mathematical study of continuous change. While algebra gives us static snapshots, calculus provides the movie of how things move and evolve. We begin with the derivative. Geometrically, it is the slope of a curve at a single point. Imagine a function like f of x equals x squared. The derivative, written as f prime, tells us the instantaneous rate of change. For x squared, the power rule tells us the derivative is simply 2x. But functions are often nested inside each other. This is where the chain rule becomes essential. It allows us to differentiate a function of a function, like f of g of x. We multiply the derivative of the outer function by the derivative of the inner function. In deep learning, the chain rule is the secret engine behind backpropagation. Finally, when we deal with multiple dimensions, we use partial derivatives. Imagine a surface defined by x and y. A partial derivative with respect to x measures how the function changes as we move along x, while holding the variable y completely constant. This concept allows AI to optimize high-dimensional cost functions through gradient descent. From simple slopes to complex optimization, calculus is the language of optimization. Thanks for watching. Probability and statistics are the bedrock of machine learning. They allow us to quantify uncertainty and find patterns in noisy data. We start with the basics of data description: mean, variance, and standard deviation. The mean is the average, the center of gravity for our data points. Variance measures the spread, how far the numbers are stretched from that center. The standard deviation is simply the square root of variance, bringing the spread back to the original units. Next, we look at distributions, specifically the normal distribution, or bell curve. Most natural phenomena, from heights to test scores, follow this pattern. It is defined by its peak at the mean and its width, governed by the standard deviation. In AI, we often assume our data or errors follow this distribution to simplify calculations. Finally, we reach the cornerstone of logical inference, Bayes' theorem. It provides a mathematical way to update our beliefs as we gather new evidence. The probability of a given B depends on the probability of B given A, multiplied by our prior knowledge. This theorem is the heart of spam filters, medical diagnosis, and autonomous driving. From measuring the average to updating our worldview with data, statistics is the science of making sense of the world. Thanks for watching. Welcome. Today we are exploring the fundamental building block of all deep learning, the artificial neuron, also known as a perceptron. Let's look inside. A neuron takes in data, called inputs, represented as x1, x2, and x3. Each input is multiplied by a weight, which determines how important that input is. We also add a bias term, which shifts the result up or down independently of the inputs. The neuron computes the weighted sum of all inputs plus the bias. Let's call this sum z. But if we stop here, our network is just a linear model. To solve complex problems, we pass z through an activation function. First is the sigmoid function. It squashes any input into a value between 0 and 1, forming an S-shaped curve. It's great for predicting probabilities. Next is tan. It's similar to sigmoid, but it squashes values between -1 and 1, which helps center the data around 0. Finally, we have ReLU, or rectified linear unit. It simply outputs 0 if the input is negative, and outputs the raw value if it's positive. Despite being so simple, ReLU is the standard activation function in modern neural networks because it trains incredibly fast and prevents vanishing gradients. To summarize, weights and biases calculate the signal, and activation functions decide if the neuron fires. Thanks for watching. Welcome back. Today we are exploring the heartbeat of neural networks, forward propagation and backpropagation. Think of a neural network learning like a student taking a test. First, the student makes a guess. This is forward propagation. Data flows forward from the input layer, through the hidden layers, to the output layer. Each neuron multiplies inputs by weights, adds a bias, and applies an activation function to generate a prediction. But how do we know if the prediction is right? We use a loss function. It compares our network's guess to the actual true answer, calculating the total error. If forward propagation is taking the test, backpropagation is reviewing the graded test to see what went wrong. The network works backwards from the output to the input. Using calculus, specifically the chain rule, it calculates the gradient. Gradients tell us exactly how much each individual weight and bias contributed to the overall error. Finally, an optimizer like gradient descent uses these gradients to update the weights. It nudges them down the slope, minimizing the loss for the next time. Forward to predict, backward to learn. Iterating this cycle is how AI achieves mastery. Thanks for watching. Welcome to a comprehensive deep dive into the compass that guides all machine learning models, loss functions. Today, we are exploring the three mathematical engines of AI learning: mean squared error, cross-entropy, and KL divergence. Without a loss function, a neural network is effectively blind. It's just a random number generator. The loss function calculates exactly how wrong the model is, providing the critical mathematical feedback, or gradients, needed to improve and learn. Let's begin with the absolute gold standard for continuous regression tasks, mean squared error, commonly known as MSE. Imagine you are building an AI model to predict real estate prices. The true value of a house is $300,000. Your model makes a prediction, let's call it Y hat, of $200,000. The error is the difference between these two numbers. But why do we calculate the squared error? MSE takes the difference and squares it. This accomplishes two brilliant things. First, squaring the number ensures the result is always positive, meaning overestimating and underestimating don't cancel each other out. Second, and most importantly, it heavily punishes large errors. An error of 2 becomes a penalty of 4, but an error of 10 becomes a massive penalty of 100. Graphically, this creates a beautiful, smooth, U-shaped parabola. This smooth curve acts like a bowl, gently guiding the model's optimizer safely down to the minimum possible loss. However, MSE has a fatal weakness. It is completely terrible for classification tasks. If you want to classify whether an image is a dog or a cat, MSE struggles because classes don't have mathematical distances. For classification, we use cross-entropy. In classification, neural networks don't output hard labels, they output probability distributions. For example, the model says there is a 90% chance the image is a cat, and a 10% chance it is a dog. Cross-entropy, which has deep roots in information theory, measures the difference between the model's predicted probabilities and the actual true labels. The true label is typically a one-hot encoded vector, 100% for the correct answer, and 0% for everything else. The core of cross-entropy is the natural logarithm. It calculates the surprise of the prediction. If the model is 99% confident it's a dog, and it is a dog, the loss is near zero. The model is barely penalized. But, if the model is 99% confident it's a cat, and it's actually a dog, cross-entropy applies a devastating, exponentially massive penalty. It screams at the model, you weren't just wrong, you were confidently wrong. This forces the model to rapidly correct bad assumptions. This brings us to a very close mathematical cousin of cross-entropy, Kullback-Leibler divergence, or KL divergence for short. While cross-entropy calculates the total surprise, KL divergence measures the extra surprise. It strictly answers the question, how much information is lost when we use our model's probability distribution, Q, to approximate the true probability distribution, P? Visually, imagine two bell curves. KL divergence calculates how far apart these two distributions are, and specifically measures how to reshape the predicted curve to perfectly match the target curve. But remember, it is asymmetric. Walking from distribution P to Q yields a different divergence than walking from Q to P. KL divergence is heavily used in generative AI, specifically in variational autoencoders. It forces the AI's internal latent space to match a clean, standard normal distribution, preventing the model from just memorizing data, and forcing it to learn meaningful, continuous representations of the world. To summarize this deep dive, use mean squared error when your AI is predicting continuous numbers, like prices or temperatures. Use cross-entropy when you are classifying discrete categories, like words or images. And use KL divergence when you need to match and mold complex probability distributions, especially in generative AI. Welcome! Today we explore the engines that power deep learning, optimizers. We will compare three heavyweights, stochastic gradient descent, RMSprop, and Atom. Let's start with stochastic gradient descent, or SGD. Imagine navigating a hilly landscape blindfolded. You feel the slope and take a step downhill. SGD calculates the gradient on a mini batch of data. But in narrow ravines, SGD bounces back and forth erratically, making very slow progress toward the minimum. To fix this, researchers introduced RMSprop. Instead of a single global learning rate, RMSprop adapts the step size for every single parameter. It divides the learning rate by a moving average of squared gradients. This dampens the steep oscillations and accelerates progress along flat directions, smoothing out the journey. Finally, we have Atom, which stands for Adaptive Moment Estimation. Atom combines the best of both worlds. It uses the adaptive learning rates from RMSprop, and adds momentum, which remembers previous steps to build up speed in consistent directions. This allows Atom to glide smoothly and quickly to the minimum. In summary, SGD is simple but can be slow. RMSprop is great at taming erratic gradients. Atom combines momentum and adaptability, making it the robust, go-to-default for modern AI. Thanks for watching. Have you heard of the Muon optimizer? It is a brand new algorithm that is setting speed records in training large language models. Traditionally, optimizers like AdamW treat all parameters the same. But neural networks contain massive 2D weight matrices in their hidden layers. Muon, which stands for momentum orthogonalized by Newton-Schultz, treats these 2D matrices differently. Instead of a standard update, it applies a Newton-Schultz iteration. This forces the momentum update to become orthogonal, making each training step highly efficient. In practice, it is a hybrid approach. You use Muon strictly for the heavy 2D hidden weights, and keep standard AdamW for the 1D biases and embeddings. By perfectly tuning updates for matrices, Muon trains models faster and cheaper. Thanks for watching. Supervised learning is the most common form of machine learning. It is like learning with a teacher. We provide the model with input data and the correct answers, called labels. The first major algorithm is linear regression. We use it when we want to predict a continuous number, like the price of a house based on its size. The goal is to find the line of best fit that minimizes the distance between the line and our data points. The formula is simple: y equals weight times x plus bias. But what if we want to classify things? That is where logistic regression comes in. Despite the name, it is used for classification, like determining if an email is spam or not spam. Instead of a straight line, it uses the sigmoid function to squash any value into a probability between 0 and 1. If the probability is above 0.5, we classify it as 1, otherwise, it is 0. Whether predicting prices or classifying emails, these two algorithms are the foundation of supervised learning. Thanks for watching. In the world of machine learning, we often need to organize data. This is done through two main approaches: classification, where we know the categories, and clustering, where we let the machine find the groups itself. Let's start with k-nearest neighbors, or KNN. It is one of the simplest classification algorithms. Imagine we have a new data point. To decide its category, we look at its k closest neighbors. If most of those neighbors are red, the new point becomes red. It is literally a majority vote based on distance. Next, we have support vector machines, or SVMs. Instead of looking at neighbors, an SVM tries to draw a boundary, called a hyperplane, that maximizes the distance between two classes. The points closest to this boundary are the support vectors. By maximizing this margin, the model becomes more robust to new, unseen data. Even if data isn't linearly separable, SVMs can use the kernel trick to project data into higher dimensions to find a split. Now, let's move to unsupervised learning with k-means clustering. Here, we have no labels, just raw data. We want the computer to find k distinct clusters. The algorithm starts by placing k random center points, called centroids. It then assigns every data point to its nearest centroid. Next, it moves the centroids to the average center of their assigned points and repeats the process. Eventually, the centroids stop moving, and we have our clusters. From the voting logic of KNN to the geometric boundaries of SVMs and the iterative grouping of k-means, these tools allow us to make sense of complex datasets. Thanks for watching. Welcome. Today we are looking at feature engineering, specifically scaling, normalization, and PCA. Let's start with scaling. Imagine you have two features: age, which goes from 0 to 100, and income, which goes up to $100,000. Machine learning models can get confused and think income is vastly more important just because the raw numbers are bigger. Min-max scaling fixes this. It mathematically squishes all values into a tiny, uniform box, forcing everything to sit exactly between 0 and 1. Now, age and income are on equal footing. Next up is normalization, also known as standardization. Sometimes your data is spread out wildly with extreme outliers that confuse your model. Standardization gathers your data and molds it into a beautiful bell curve. It forces the mean to exactly 0, and the standard deviation to exactly 1. This helps gradient descent converge much faster. Finally, what if you have too many features? This causes the curse of dimensionality, slowing down training and causing overfitting. Principal Component Analysis, or PCA, solves this beautifully. It rotates the perspective of your data to find the path of maximum variance. We can take a messy two-dimensional scatter plot, find the main axis, and project it down to a single, one-dimensional line without losing the big picture. Proper feature engineering makes your models faster, smarter, and far more accurate. Thanks for watching. Decision trees and random forests are among the most intuitive and powerful tools in machine learning. They mimic the way humans make decisions by asking a series of questions. A decision tree starts with a single node, called the root. From there, it splits into branches based on specific features of the data. Each internal node represents a question, like, is the temperature above 30 degrees? The final nodes are called leaves, which provide the prediction, such as yes, it will rain, or no, it won't. However, a single decision tree has a major weakness: overfitting. It can become so complex and specific to the training data that it fails to generalize to new information. To solve this, we use a random forest. Instead of relying on one tree, we build an ensemble of many trees. Each tree is trained on a random subset of the data and a random subset of features. This diversity ensures that the trees don't all make the same mistakes. When it's time to make a prediction, every tree in the forest gets a vote. The random forest takes the majority vote for classification, or the average for regression. This wisdom of the crowd makes the model incredibly robust and accurate. From simple flowcharts to massive ensembles, these algorithms are the workhorses of modern data science. Thanks for watching. Welcome. Today we are exploring gradient boosting machines and comparing three absolute titans: XGBoost, LightGBM, and CatBoost. But first, what is gradient boosting? It is an ensemble learning technique. Instead of training one massive model, it combines many weak learners, which are typically simple decision trees. Each new tree is trained specifically to correct the errors, or gradients, made by the previous trees. They work together like a team, sequentially improving the final prediction. Let's look at the first titan, XGBoost, or Extreme Gradient Boosting. Created by Tianqi Qin in 2014, it quickly became the king of Kaggle competitions. XGBoost's superpower is its mathematical rigor. It uses second-order gradients and advanced regularization to aggressively prevent overfitting. It is the gold standard for robust, accurate predictions. Next up is LightGBM, developed by Microsoft. As datasets grew massive, XGBoost could be slow. LightGBM solved this by focusing on shear speed. Instead of growing trees level by level, it grows them leaf by leaf. Combined with histogram-based splitting, LightGBM trains incredibly fast while using much less memory. Finally, we have CatBoost, created by Yandex. In many real-world datasets, we have categorical data, like text labels or IDs, which normally require tedious preprocessing. CatBoost handles categories natively, without needing one-hot encoding. It also uses a brilliant technique called ordered boosting to prevent data leakage, making it incredibly accurate out of the box. To summarize, use XGBoost for battle-tested robustness, LightGBM for massive datasets and speed, and CatBoost when dealing with a lot of categorical variables. Thanks for watching. Welcome. Let's explore how we evaluate machine learning models. We'll cover overfitting, underfitting, the bias variance trade-off, and cross-validation. Imagine fitting a curve to data points. If our model is too simple, it ignores patterns. This is underfitting. If it's too complex, it memorizes the noise, hitting every point but failing on new data. This is overfitting. We want the Goldilocks zone, a good fit. This brings us to the bias variance trade-off. Underfitting means high bias, the model makes strong, incorrect assumptions. Overfitting means high variance, the model is too sensitive to the training data. As complexity increases, bias drops but variance spikes. The total error forms a U-shape. The lowest point is our sweet spot. So, how do we find this sweet spot safely without memorizing our test data? We use cross-validation. Instead of one train test split, we divide our data into k-equal chunks, or folds. In 5-fold cross-validation, we train our model on 4 folds, and test it on the remaining one. Then, we rotate the test fold. We repeat this process until every single fold has been used as the test set. Averaging these 5 scores gives us a highly reliable measure of true performance. Mastering the bias variance trade-off with cross-validation is the key to building reliable AI models. Thanks for watching. Once text is tokenized, the AI still needs to understand the meaning of those tokens. This is where word embeddings come in, turning words into high-dimensional numerical vectors. Imagine a massive mathematical space. In this semantic space, words with similar meanings are placed physically close to each other. But it's more than just location, it's about relationships. This space is famous for its vector math. If you take the vector for king, subtract man, and add woman, the resulting point is almost exactly at queen. One of the first breakthroughs was Word2Vec, released by Google in 2013. It uses a shallow neural network to learn word meanings by predicting context. Whether using CBOW to predict a word from its neighbors, or skipgram to predict neighbors from a word, it learns that words appearing in similar spots must have similar meanings. Then came GLOVE, or Global Vectors, from Stanford. While Word2Vec looks at local windows of text, GLOVE looks at the whole dataset at once. It builds a massive co-occurrence matrix to see how often every word appears with every other word. By factorizing this matrix, it creates vectors that capture global statistical relationships across the entire library. Today's large language models use even more advanced versions, where vectors can have thousands of dimensions. This allows AI to understand irony, synonyms, and complex concepts as simple geometric relationships. Word embeddings are the true soul of AI's language understanding. Thanks for watching. Welcome to a comprehensive masterclass on deep learning architectures. Today, we are undertaking a massive deep dive into the two most important specialized neural networks ever created. First, convolutional neural networks, or CNNs, which gave AI the ability to see and understand the visual world. And second, recurrent neural networks, or RNNs, including LSTMs and GRUs, which gave AI the ability to process time, sequence, and language. Let us begin with vision. Why do we need a special architecture for images? Imagine feeding a high-definition image into a standard, fully connected neural network. A 1080p color image has over 6 million individual data points. If your first hidden layer has just 1,000 neurons, you are forcing the network to calculate 6 billion weights instantly. The memory requirement is astronomically prohibitive. Furthermore, a standard network flattens the image into a 1D line. This destroys all 2D spatial relationships. A cat's ear is made of pixels that are spatially next to each other. If we flatten the image, we lose that vital geometric structure. To solve this, researchers introduced the convolution operation. Instead of connecting every pixel to every neuron, a CNN uses a tiny matrix called a filter, or a kernel. Typically, this is a 3x3 grid of weights. The network slides, or convolves, this tiny filter across the entire image, pixel by pixel. At every single stop, it performs a dot product. It multiplies the filter's weights by the pixels directly underneath it, and sums them into a single number. What is the magical result of this? Feature extraction. By learning the exact right weights, a filter becomes an edge detector. It might light up when it sees a vertical line, or a horizontal curve. As we stack layer upon layer of these convolutions, the network combines simple edges into textures, textures into shapes, and shapes into complex objects like faces and cars. Because the filter slides across the whole image, a cat recognized in the top left corner will still be recognized if it moves to the bottom right. This is called translation invariance. However, as we extract thousands of feature maps, our data size explodes. We need to aggressively downsample the spatial dimensions. Enter the pooling layer. The most dominant technique is max pooling. Imagine a 2x2 window sliding over our feature map. Instead of doing complex math, max pooling simply looks at the 4 numbers in the window, keeps the highest value, and throws the rest in the trash. This halves the height and halves the width of the data, dramatically reducing the computational load, while preserving the most highly activated, dominant features in that region. A CNN is simply a repeating sandwich of convolutions to extract features, and pooling to compress them, ending with a standard classification layer. But what if our data is not a static grid of pixels? What if it unfolds over time? Think of a sentence, a spoken audio wavelength, or the daily fluctuations of the stock market. Standard feed-forward networks have severe amnesia. They process each input in total isolation. They have zero concept of time or memory. Recurrent neural networks, or RNNs, solve this by introducing a temporal loop. When an RNN processes time step 1, it generates a prediction, but crucially, it also generates a hidden state. This hidden state acts as the network's short-term memory. When time step 2 arrives, the RNN takes the new input and the hidden state from step 1. We can visualize this by unrolling the network across time. Input 1 goes into cell 1, which passes its hidden state to cell 2. Input 2 goes into cell 2, which passes its state to cell 3, forming an unbroken chain of temporal context. In theory, this is perfect. In reality, standard RNNs suffer from a catastrophic mathematical flaw known as the vanishing gradient problem. During training, the network uses backpropagation through time to update its weights. The error gradient must flow backwards through every single time step. Because the gradient is repeatedly multiplied by weight matrices, if those numbers are less than 1, the gradient shrinks exponentially. Within 10 or 20 steps, the gradient vanishes to 0. The network completely forgets early context. If a paragraph begins with "I was born in France" and ends 100 words later with "I speak fluent," a standard RNN cannot remember France to predict French. To cure this catastrophic amnesia, Sepp Hochreiter and Jürgen Schmid-Huber created a masterpiece in 1997, the Long Short-Term Memory Network, or LSTM. LSTMs fundamentally redesign the internal structure of the RNN cell. They introduce an entirely new pathway called the cell state. Think of the cell state as an express highway, or a conveyor belt, running straight down the entire length of the sequence. It carries long-term memory with minimal interference, completely bypassing the vanishing gradient problem. How does the LSTM protect this conveyor belt? It uses 3 mathematical valves called gates, built using sigmoid neural layers. First is the forget gate. It looks at the new input and the old hidden state, and decides what outdated information on the conveyor belt should be erased. Second is the input gate. It decides what brand new, relevant information from the current step should be written onto the conveyor belt. Third is the output gate. It filters the conveyor belt to decide exactly what the cell should output as a prediction, and what it should pass as the hidden state to the next cell. By explicitly learning what to keep, what to throw away, and what to read, LSTMs can remember context across thousands of time steps. Years later, researchers created a streamlined variant called the Gated Recurrent Unit, or GRU. The GRU simplifies the architecture by merging the cell state and hidden state into one pathway. It also merges the forget and input gates into a single update gate. Because it has fewer tensor operations, a GRU trains significantly faster and uses less memory, while often matching the LSTM's performance on a vast majority of sequential tasks. Let us summarize this expansive masterclass. When your data contains 2D spatial relationships, like pixels in photography or medical imaging, rely on convolutional neural networks. They use filters to find patterns, and pooling to compress them. When your data flows sequentially through time, like written text, spoken audio, or financial charts, rely on recurrent neural networks. Specifically, use LSTMs or GRUs to defeat the vanishing gradient problem and allow your AI to master long-term memory. Thank you for joining this deep dive into the architecture of modern AI. What is a large language model? It is an AI system trained on huge amounts of text. It learns patterns, then predicts the next token or word. That is how it can draft, summarize, and answer in plain language. The large part refers to scale. More parameters give the model more capacity to store relationships. The language part means context matters. It works with words, sentences, and nearby clues to stay coherent. Put together, it is a fast text assistant, not a human mind. But it can still be very useful for writing and learning. How do companies actually build a large language model from scratch? Building a modern AI assistant is a massive engineering feat that happens in 4 major stages. Stage 1 is data collection and preparation. First, you scrape trillions of words from the public internet, books, and code repositories. Then, you clean the data to remove spam and toxic content. Finally, you chop the text into numerical pieces called tokens. Stage 2 is pre-training. This is the hardest and most expensive phase. Using thousands of GPUs running for months, the model simply learns to predict the next token. The result is a base model. It has a massive brain full of world knowledge, but it doesn't know how to chat yet. Stage 3 is supervised fine-tuning, or SFT. Now, we show the base model thousands of high-quality question and answer pairs written by humans. This teaches the model how to follow instructions, act as an assistant, and format its text properly. Stage 4 is alignment, often done using RLHF reinforcement learning from human feedback. Humans grade the model's answers, giving a thumbs up to good responses and a thumbs down to bad ones. This final polish makes the model helpful, honest, and harmless. To summarize, we gather data, pre-train a base model, fine-tune it for instructions, and align it with human values. That is the complete pipeline to build an LLM. Thanks for watching. What is the difference between pre-training and fine-tuning? Think of it like school. Pre-training is general education. Fine-tuning is specialization. Pre-training means learning from massive amounts of data. The model reads billions of pages to understand grammar, facts, and reasoning. It builds a broad foundation of knowledge about how language works. Fine-tuning means training on a focused dataset. You take the pre-trained model and teach it a specific task. It could be medical questions, legal documents, or customer support. The model already knows language. Now it learns your domain. Here is a simple analogy. Pre-training is like learning to drive in general. Fine-tuning is like learning to drive a race car on a track. Same core skill, different context and goals. Pre-training is expensive. It needs thousands of GPUs and weeks of compute. Fine-tuning is cheaper. It runs on fewer GPUs and takes hours or days. So the key idea is this. Pre-training builds the foundation. Fine-tuning shapes it for your needs. Together, they make modern AI both powerful and practical. Thanks for watching. Next up, how transformers actually work. What exactly is a tokenizer, and why do AI models need them? Simply put, AI models cannot read text, they only understand numbers. A tokenizer is the bridge between human language and machine math. It takes raw text and chops it into smaller pieces called tokens. Each unique token is then assigned a specific number, known as a token ID, allowing the AI to process it. There are 3 main types of tokenizers. First is word-based tokenization. This splits text by spaces. For example, I love AI becomes 3 tokens. It is simple, but it creates a massive dictionary, and struggles when you encounter punctuation or misspelled words. Second is character-based tokenization. This breaks text down into individual letters. While it handles misspellings easily and keeps the vocabulary small, it completely destroys the meaning of words, and creates sequences that are way too long for the AI to handle efficiently. This brings us to the modern standard, subword tokenization. Methods like byte pair encoding, or BPE, break words into meaningful chunks. For example, a rare word like unbelievably might be split into un, believe, and ably. Subword tokenization is the best of both worlds. It keeps the vocabulary at a reasonable size, handles rare words perfectly without errors, and preserves meaning. This is exactly what models like GPT and BERT use today. Understanding tokenization is the very first step in understanding how AI processes language. Thanks for watching. Welcome back. Today, we are taking a deep dive into byte pair encoding, or BPE. It is the core tokenization algorithm that powers modern large language models like GPT-4, Claude, and Llama. But what is it, and how does it actually work? Let's start with a bit of history. Did you know BPE was not originally invented for artificial intelligence? It was created in 1994 by a programmer named Philip Gage as a general data compression technique. The original goal was simply to shrink the size of text files to save disk space in memory. How did it compress data? Let's look at a visual example. Imagine a simple text string, A, B, C, A, B. The algorithm scans the string and looks for the most frequent pair of adjacent characters. Here, the pair AB appears 4 times. BPE creates a new rule: replace all AB pairs with a new, unused symbol, like X. Our 9-character string instantly shrinks to X, C, X, but BPE doesn't stop there. It loops again. Now, it sees the pair XX appears twice. It makes a new rule: replace XX with Y. Our string becomes Y. Through these iterations, we compress 9 characters down to just 3. So, how did a 1994 compression algorithm become the heart of modern AI? Fast forward to 2015. AI researchers realized that human language has highly repetitive patterns. Prefixes like un, or suffixes like ing and est, appear constantly. By using BPE, AI could compress letters into meaningful subwords. This solved a massive issue called the out-of-vocabulary problem. Before BPE, if an AI saw a rare or made-up word, it would crash or output an unknown error. With BPE, if it sees a new word like lowest, it doesn't panic. It just breaks it down into known subwords, like low and est. Let's walk through a practical example of how BPE trains its vocabulary for an LLM. We start with a base vocabulary of individual characters, L, O, W, E, R, S, T. The algorithm scans our dataset and counts pairs. It finds that E and R appear together very frequently. It merges them, adding the new subword to our vocabulary. On the next loop, it finds E and S, creating the token ES. On the next loop, it merges ES and T to create the suffix est. Iteration by iteration, BPE builds a highly efficient dictionary of subwords, finding the perfect balance between individual characters and whole words. And that is exactly how byte pair encoding teaches your AI to read. Thanks for watching. While byte pair encoding is extremely popular, it's not the only way AI reads. Today, we explore wordpiece and sentencepiece, 2 powerful tokenization methods that handle language in very different ways. First, let's look at wordpiece. This was made famous by Google's BERT model. At first glance, it looks exactly like BPE. It merges characters into subwords. However, the internal logic is different. While BPE merges the most frequent pair of symbols, wordpiece merges the pair that maximizes the likelihood of the training data. In simple terms, it asks, if I merge these two, how much better does the model understand the overall language? It also uses a special double hash prefix, like ##ing, to show that a token is a suffix of a larger word. Next, we have sentencepiece. This is the modern standard for models like T5, Albert, and Llama. The biggest problem with BPE and wordpiece is that they assume words are always separated by spaces. But in languages like Chinese or Japanese, there are no spaces. Sentencepiece solves this by treating the entire sentence as a raw stream of characters. It treats the whitespace itself as a special symbol, usually represented by an underscore. Because it doesn't need to pre-split text by spaces, it is truly language agnostic. It can be trained directly on raw text, making it incredibly robust for multilingual AI. To summarize our toolkit, BPE uses frequency and is the GPT standard. Wordpiece uses likelihood and is the BERT standard. And sentencepiece uses raw streams with spaces as symbols, making it the multilingual champion. Choosing the right tokenizer is vital for model performance. Thanks for watching. Welcome. Today we are exploring one of the most brilliant tricks in the transformer architecture, positional encoding. To understand why we need it, we must understand a flaw in transformers. Unlike older AI models that read text sequentially word by word, transformers process all words in a sentence at the exact same time. This parallel processing makes them blazing fast, but it completely destroys word order. To a basic transformer, dog bites man and man bites dog look exactly the same, like a scrambled bag of words. To fix this, researchers introduced positional encoding. The idea is to inject a unique mathematical signature into every words vector, acting like a timestamp or a GPS coordinate. But they didn't just use simple numbers like 1, 2, 3. Instead, they used intersecting sine and cosine waves of different frequencies. Imagine a set of continuous waves flowing through the sentence. By reading the exact height of the various waves at position 1, position 2, and so on, the model gets a highly unique, continuous positional vector for every single slot. Why use sine and cosine waves? Because waves are continuous and periodic. This beautiful mathematical property allows the model to easily calculate the relative distance between any two words. It also allows the model to perfectly generalize to sentences longer than it has ever seen during training. Finally, how is it applied? It is beautifully simple. The model takes the original word embedding vector, which contains the meaning of the word. Then, it simply adds the positional encoding vector, which contains the order. The resulting final vector is passed into the network, containing both rich meaning and exact position. And that is how transformers maintain word order. Thanks for watching. Welcome back. Inside every transformer block, there are two unsung heroes that make deep AI models possible: residual connections and layer normalization. To understand why we need them, we must look at the biggest problem in deep neural networks. When you stack dozens of layers on top of each other, data gets multiplied over and over. Eventually, the numbers either shrink to zero, which is called a vanishing gradient, or explode to infinity, completely destroying the network's ability to learn. Enter the first hero, the residual connection, also known as a skip connection. Instead of forcing data to only travel through the complex neural network layer, we build a shortcut. Mathematically, it is beautifully simple. The input x flows into the layer to become f of x. But simultaneously, x takes the bypass lane around the layer. At the end, they are added together. The output is x plus f of x. This guarantees that the original information is never lost, no matter how deep the network gets. But we still have a problem. If we keep adding numbers together, they will grow larger and larger, making the network unstable. This is where layer normalization steps in as the great stabilizer. Layer normalization takes a wild, unbalanced list of numbers and mathematically wrangles them. It calculates the mean and variance across the layer, and scales the numbers so they always center around zero. This perfectly balances the flow of data, keeping the network mathematically stable. In the famous transformer diagram, these two concepts are combined into the add-in norm step. Data goes through self-attention, gets added to the residual shortcut, and then normalized. The same process repeats for the feed-forward network. Together, residual connections and layer normalization are the architectural glue that holds massive AI models together. Thanks for watching. What are transformers? They are the deep learning architecture that changed artificial intelligence forever. Introduced in 2017 by Google in the paper "Attention is All You Need," they replace slow, sequential models with a system that processes data in parallel. Let's draw the full architecture. It consists of two main halves, the encoder block on the left, and the decoder block on the right. Let's break down exactly how data flows through them. Step 1 is tokenization and embedding. The input text is mapped into high-dimensional numerical vectors. This translates human language into math, capturing the core meaning of the words. Step 2 is positional encoding. Because transformers process all words at once, they lose the order of the sentence. Positional encoding fixes this by adding mathematical sine and cosine wave patterns to the vectors. Step 3 is the true magic, the self-attention mechanism. This allows the model to figure out how every word relates to every other word. It uses query, key, and value matrices to analyze contextual relationships from multiple angles. Step 4 is the full encoder stack. By passing data through attention and feed-forward neural networks, the encoder outputs a deeply contextualized representation of the original input. Step 5 is the decoder. It uses masked self-attention to prevent cheating by looking into the future, and cross-attention to look back at the encoder's context. Finally, linear and softmax layers generate the output sequence one token at a time. Today, this architecture has splintered into specialized models. Models like BERT use only the encoder block to deeply understand text. Meanwhile, models like GPT use only the decoder block to auto-regressively generate entirely new text. Together, these form the foundation of all modern large language models. Thanks for watching. What is the exact difference between an encoder and a decoder? In modern AI, these are the two fundamental engines that power large language models. Let's break down their mechanics in deep detail. Let's start with the encoder. Think of the encoder as the reader. Its primary job is to process the input text and build a deep, rich contextual understanding of it. The defining feature of the encoder is that it reads bidirectionally. This means its self-attention mechanism looks at the entire sequence at once. It looks both left and right to understand how words relate to their surrounding context. Models that only use an encoder, like BERT, excel at tasks like document classification and sentiment analysis. Now, let's look at the decoder. Think of the decoder as the writer or generator. Its primary job is to produce new text, outputting one token at a time. Unlike the encoder, the decoder is strictly unidirectional and autoregressive. It uses a mechanism called masked attention. This means it can only look at the words it has already generated, and it is completely blind to the future. Models that only use a decoder, like GPT, are the powerhouse behind modern chatbots and text generation. But what happens when you combine them? In the original sequence-to-sequence transformer, they work together via cross-attention. The encoder processes the source language into a context vector. Then, the decoder generates the translated text, constantly looking back at the encoder's context to know what to write next. To summarize, the encoder is for understanding, reads bidirectionally, and powers models like BERT. The decoder is for generation, reads unidirectionally, and powers models like GPT. Knowing the difference gives you the keys to understanding modern AI architectures. Thanks for watching. You asked about two of the most critical concepts in modern AI, autoregressive generation and the self-attention mechanism. Let's break down exactly what these terms mean visually. First, what does autoregressive mean? In statistics and AI, auto means self, and regressive means predicting the next step. So, an autoregressive model predicts the next word in a sequence based on its own past outputs. Imagine a model generating a sentence. It starts with a prompt and predicts the word the. Then, it takes that output, loops it back as the new input, and predicts cat. It repeats this loop, taking the past to generate the future, one single word at a time. It is strictly a one-way street. This is how ChatGPT writes its answers. Now, what is the self-attention mechanism? If autoregressive is how the model writes, self-attention is how the model thinks. It is how the model understands the context and relationships between words in a sequence. Take these two sentences, the bank of the river and the bank on the corner. How does the model know that bank means land in the first and a building in the second? By paying attention to the surrounding words. The word river dynamically alters the mathematical meaning of the word bank. It does this using three mathematical matrices: query, key, and value. Think of the query as a word asking, what context do I need to understand myself? The key is other words saying, here is the context I contain. When a query and key match, the model transfers the actual meaning, the value, between the words. To summarize, autoregressive generation is the step-by-step writing process. Self-attention is the interconnected web of context that makes the writing make sense. Together, they are the secret recipe behind modern language models. Thanks for watching. Have you ever wondered how ChatGPT actually works? At its core is a model called GPT, which stands for Generative Pre-trained Transformer. Unlike the original transformer that had two halves, GPT is a decoder-only architecture. It completely drops the encoder, relying entirely on a powerful stack of decoder blocks. Because it only has a decoder, it specializes entirely in generating text. It does this using a simple rule: predict the next word. When you give it a prompt like "the sky is," it calculates probabilities and outputs blue. Then, it takes blue, loops it back into the input, and predicts the next word. This loop is called autoregressive generation. To understand its true power, let's look at the famous GPT-3 architecture. GPT-3 isn't doing anything fundamentally different, it is just doing it at an unimaginable scale. It was built with a staggering 175 billion parameters. Think of parameters as the artificial synapses or neural connections in its brain. It was trained on 300 billion tokens, which is essentially the entire public internet, books, and articles. Physically, this looks like 96 massive decoder layers stacked on top of each other. And it uses 96 attention heads to look for context in thousands of words simultaneously. So, a simple objective, predicting the next word. Combined with massive layers, parameters, and data. This perfectly forms the emergent intelligence and reasoning we see today. That is how GPT works. Thanks for watching. Zero-shot versus few-shot learning. What is the difference? In zero-shot learning, you ask the AI to perform a task without giving it any examples. You simply provide the instruction, like translate apple to Spanish, and the model uses its base knowledge to answer. In few-shot learning, you give the AI a few examples first to show it exactly the pattern you want. You might show dog becomes Pero, and cat becomes Gato. Then you ask for apple. Seeing the pattern, the model provides a highly accurate, properly formatted response. To summarize, zero-shot uses zero examples and relies purely on general knowledge. Few-shot uses a small set of examples to perfectly steer the model towards your specific goal. Thanks for watching. What is emergent behavior in AI? Simply put, it's when a system develops complex abilities that it was never explicitly programmed to do. For example, we train large language models on a very simple rule: just predict the next word. But as we add billions of parameters and scale up the data, something magical happens. The model suddenly learns to translate languages, write code, and solve logic puzzles. These skills weren't programmed, they emerged purely from scale. Thanks for watching.